Okay, so welcome to the CHASC, probably the last CHASC talk of the year, of the season, whatever. And it's being given by Adithya, who is a grad student at Manipal Center for Natural Sciences in Udupi, near Udupi. Most people will have heard about Udupi because it is really the epicenter of good Indian food. There are several Udupi restaurants in this area. So anyway, and we are going to try and start on time, too late, and finish on time because we get kicked out at 1 o'clock sharp here. So we'll try to. I will try to keep interruptions to a minimum. So Aditya, take it away.
Yes. Hi everyone, myself Adithya. I'm a second year PhD student, as just introduced by Vinay, from India. So basically my PhD thesis on studying solar flare triggers under supervision, my under guidance of Dr. Srijit. And I was also previously working with the Hinode images, segmentation and irradiance variability. There are one work was pending always, like this detection of XBPs. So that I'm going to discuss, and some part with flare precursors also I'm going to discuss. So here at CFA, I'm a visiting student. It's hosted by Vinay. I first thank Vinay for giving me an opportunity, and I'll thank you guys in advance for giving me the opportunity to discuss my problems with you. Would like to get good feedbacks from you guys. Maybe very critical. I don't mind. Yes. So outline of my presentation is like I'll be discussing about X-ray breakpoints. XBP is X-ray breakpoints. What are those, and how we are detecting it, and what is actually the problem I'm facing. And also similarly in flare precursors part also, what are flares and how we are analyzing them, and what is actually a problem I'm facing. So the very first part is the X-ray breakpoints. It's also called coronal breakpoints. We can see them in like AA images also, the lower corona part. So these are actually the bright like unresolved structures on a solar corona. Their size can vary from 5 arc-second to 30 arc-second. So we see them all over the disk. It's like where active regions have some restriction, lateral restriction, whereas XBPs we can see all over the disk. So you can see some regions are shown here. So very point-like structures. They are unresolved. So we are basically studying them in Hinode XRT image. Hinode XRT is a Japanese-based telescope. It observes the solar corona in X-ray band, soft X-ray mainly. So here I show the sample image, and these are the bright points what I'm showing them. So how to identify them? What I'm doing is I'm using the composite image from the Hinode XRT. So it has a very large dynamic range. This is a log scale image of that. So it's a composite image which has short and long exposure. So and then their exposure normals, and the unit is what we are doing is dn per second.
So for those who don't know, can you explain what composite means?
Usually, so this solar it has a very we have a very bright region like active region, and like a quite low intense region surrounding like maybe quiet regions. So one exposure covering both the features is quite difficult. So we have two or three set of images. So with the long exposure, so that we can see the dull features, and by that time these bright features will become saturated. So there will be another exposure, another short exposure image to capture these two. So and then they stitch together to make a composite image, and the exposure normals so that we can have a high dynamic range in a one single image.
We have a question.
We have it.
The question is, if they are unresolved, how do you estimate their size?
Let me answer that question. You can correct me if I'm wrong. I guess unresolved is not the right word, perhaps, Jeff. That they are featureless. So, for example, they're not loop-like. That is the important thing. I mean,
They're loop-like. They're bipolar structures. They have loop-like structures.
So then, what does unresolved mean?
like in XRT, I'm talking only in this unresolved, actually only in XRT I'm talking about.
Okay.
So if you have a high resolution, we can actually resolve them by power structures.
Okay.
So only in this part we're calling it.
Okay.
What would be an instrument that you can resolve it in? So, sorry, I don't know which instruments.
I
you
guess
use.
solar orbiter can do
Okay.
when it's during its closer approaches, and maybe there are few studies on the through the iris images also. There are actually few part when there's some counterpart we could be able to see through the iris also. And for a very bright XBPs, in a photospheric also we can see some counterpart of that as a magnetic field foot point we can have to see it.
Thank you.
So for a bright one, there are small also. For example, this can be like a bright XBPs. This one can. There are even tiny spots that we may not be able to see in photosphere, but with through solar orbiter during its closer approach, we can actually resolve that. So in order to detect them, so what we are doing is we are here. So one threshold value just to detect one threshold may not work because this background, if you see this, the level of intensity is here and here is completely different. It's slightly different. So one threshold value to select these on a threshold basis, selecting these sources quite difficult. So in that we use the package something called source extractor. So there, through that I explained this process in detail in the next step. So through that we get one round of estimation for our bright points, and then we refined with some further conditions to narrow down what are the bright points that we have.
Sorry, I know I said I won't interrupt, but I think I need to say for the sake of the solar people here, that source extractor is a very common astronomical detection technique used in optical astronomy. So
sorry, I missed it. Yes, I should have said that. Yes. So okay. So what with the what source extractor does it everything in a background. So I'm just putting it what actually it does in a few by words. So what we so for example, this is an image. So what it does, it estimates the background it estimates local background actually. So means it entire image it's divided into 32 by 32 grid and estimate the background, and it's smoothened it with a 3x3 median filter, and so that we get a smoothly varying background. And similarly, sigma is also estimated. So while estimating background, it's iteratively takes out the sigma like a three sigma values. So iterative sigma clipping based on. So that whatever above 3 sigma, it's considered that as a source. Less than that is considered that as a background. So we get a smoothly varying background, and we also have a sigma for each pixels values. So for a source detection, so above we have a local background above and sigma for each pixels we have defined. So above the 2 sigma in each region is considered a source. So and based on that source, it can generate a segmentation map. So for each segmented region is actually an excited bright points. It's a bright region, bright source. The source extract says it's a bright. We have some very significant intensity above the smoothly varying background. That's what the source extractor says. These are segmented maps, but we are getting slightly elongated structure also as a part of loop, active region loop. So that's why we did the further refinement in a Python. Like we use this segmentation map, and we consider only 95% of solar disks. We don't want to go to the limb, and there are so many other stuff comes to picture. So we just ignore whatever beyond 95% solar radius. And the small features like less than a point or PSF size also we remove them from them. And there are some elongated structure also we are getting because this active region has a loop kind of thing that also being detected as a source. So what we do in order to remove them, we fit an ellipse to that. So with a semi-major axis of 150 or more than that 150 pixels, they're like lengthy structures, we remove them. But still there are something is pending that's we need, like for example here, it's not a source, it's a part of loop structure still being detected. There are a few that's some problem I'm finding close to active region. So that I need to refine in further steps. But it's quite well be able to find the sources in all of the regions. You can see here all these detectors are bright points. So we put a red color contour to show what are the detected sources are. And so this is like a sample image. So there are 3 color contour we can see. So just to this is an active region detection with another segmentation algorithm. And here also we have something called current hole, magenta color we are putting. And the red color contour what we see, those are our sources, breakpoints, X-ray breakpoints. So this is one image, sample image taken from solar 2009. It's very much close to solar minima. So where during that time we have a very minimal activity, like from the due to the on our solar surface, like we find very small number of active regions, something like this, 1 or 2 or most likely no. Sometimes we don't find any active regions also. So that time we see entire disk is dominated by these small bright points. But the scenario changes when we go to the solar maxima. So around 2014. So solar cycle has a 11-year cycle. So close to after 5.5 years from 2009. So we see that we come to solar maxima period. We see that disk is actually occupied by these bright regions. It's called active regions. And we see there is a relatively less number of bright spots. So that's we see here. So all this you can see the number of breakpoints what we get is quite less in the solar maximum. So when we plot them, we see that the number of breakpoints what we detect is less, and it's like perfect. It's kind of anti-correlation with the solar cycle. During solar maximum, we find less number of breakpoints. During solar minima, we get a maximum number of breakpoints. But here we have an issue is that this anti-correlation may be due to 2 parts. One, so if you go to solar maxima, there is some amount of like about close 20 up to 20% of solar disk is occupied by these active regions, and there is some surrounding bright patches also. And the overall background intensity of the sun also is increased during solar maximum. So maybe there may be very small bright points hiding inside, but the surrounding intensity itself is very high. So it's making hard to find them. So that part we're not able to say that what exactly is there really there are bright points we are not able to detect them, or if breakpoints there are no breakpoints during like very minimal number of breakpoints during the solar minimum. That's the question we have. So in order to address that with upon discussion with Vinay, he suggested a few more techniques to do that. So just to show how these just to plot the histogram of that. So during solar minima and solar maxima, see in a solar minima we see that the large number of, like if you say this mode actually kind of the maximum of histogram which represent like white region or the large number of bright points, so large number of pixels are in let's say for example it's around 70 to 80 counts, whereas during maxima it shifts to the higher end. So the overall background intensity increases during solar maximum. Just we can so here is a log scale I put. So we can just to the histogram we can see that there is a increase in a background intensity during solar maximum. So one in order to tackle this this one, what we can what way possible way maybe like we'll take a one selected region, maybe like something a center of disk, we'll take a one particular region and we calculate the number density for each image maybe that may be able to show how breakpoint is varying over a solar cycle. But problem with is like these active regions will be the active region will dominate in this region. They'll keep coming, so that we can't have a one particular clean region for a breakpoint detection. So so in a one particular counting the expired breakpoints in a one particular location is quite hard to do that. So another way what we are trying to do is, so there are all these regions which are affected by active region and the active region and this is the bright region around the active region. So if we can eliminate them from the image, and the remaining image, the remaining part of image only we can count the exact bright points and see how that is varying. So we'll also account for the area variation. That's another way we are trying to go forward in this way. So we calculate a number density in a quiet region. So quiet region, what I meant is So now the region where these active regions are not much affecting it. So these, for example, even though its active region is just here, all these regions are actually affected by these active region loop structures. So if you can eliminate them, all these feature, and if you can count only number of bright points only in these regions where it's the influence of active region is quite minimal there. So and if we calculate a number density over a solar cycle, so we may be able to see the proper trend. That's what we believe. So that's why you have to select that region where these active region influence regions, these bright patches. So we calculate the max sigma estimation. From that, so here I plot the histogram for the two images here. So there are, I think the image is quite small. There are so mode plus this is a sigma estimated through this max sigma estimation. This formula we estimated. So and there are two ways I did. One with a mod plus 3 sigma in a logarithm scale. I tried once. Another one with like normal linear scale itself. So mode plus 3 sigma put the cutoff. What is the cutoff it comes for? It just plotted on histogram. So if you can set a threshold at this level and ignore all the pixels above this intensity and which are below this, only in this intensity region only will count the bright points. That will have a least effect from the active regions. That's what our plan. So the log when I do with the log 1, so that during the solar maxima, that mode plus 3 sigma in a log scale actually is try to estimate a bit higher one. So I just go on with the linear calculated one in a linear scale, mod plus 3 sigma. So sigma is calculated to this, it's a mad sigma. So we tried with the plots are quite small. So we tried with the different sigma levels. So from mode plus like for a k sigma, like for example 0.5, 1, 1.5, 2, 2.5 and 3 different values I tried. So the very first one, the black one is 0.5 sigma and 3 is mod plus 3 sigma is a blue color line. So we tried with a different sigma and in all different threshold levels, we see the so this for this plot, I use only about 100 images from the entire solar cycle. So for sampling a different part of solar cycle, so only 100 images and tried with which threshold may work. So so this is a number of bright points and number density. Number density, to calculate number density, what we are this. So after this thresholding mod plus 3, like what are the k sigma threshold, the remaining region is called the region available for X-ray breakpoint detection. So number of breakpoint detected and that region we divide to calculate the number density. So both number density and breakpoint number shows an anti-correlation. I just put on solar cycle sunspot number variation that represents the solar cycle. So we see that there is still an anti-correlation exists. So this is how the quiet sun in the region. So this quiet sun region behaves below the threshold level. So here we put a threshold, right? So how this region behaves, that's what we're trying to see that. So so there we see that there is an intensity increase during the background intensity also increase, we can see that. But after 2015 we see some drastic change because we have an light leak event started to increase in after 2015. So it's quite hard to say some about the background values after 2015 June. So maybe we can, for a background intensity, if you're looking 2008 to 2014 June, 2015 June, maybe you can say some comment or something. Then so this is an image how it looks. So this is a finally we tried with mode plus 0.5 mat sigma. So all these are actually mode plus 0.5 sigma above regions. So we are counting the bright points up away from this, like only this cyan contour is eliminated from the detection and rest all region is used for a bright point detection. So we calculate number of bright points and per area. So this entire area we use it. So number of breakpoints in this area, we calculate number density. So the number density also shows an anti-correlation. This is a number density plots. This is total number of breakpoint in quiet region. So we call this as a quiet region, including the coronal hole. This is a magenta is a coronal hole, including the coronal hole. We call that as a quiet region. So that also shows an anti-correlation. This is the number of breakpoints. So in this case, we see that there is some amount of area is lost during the solar maximum. So, but when you take an area also in account, we calculate number density. This area also is accounted. That also shows an anti-correlation. So this is what we are seeing. Maybe I'll just for the discussion part I can bring it. But problem what I'm facing right now is, so there is increase in the background also. So we are counting the breakpoints with increased enhanced background. So, but how we can tackle that? There is increased background, but number of breakpoints will decrease. It's just due to the increase only we are finding difficulty to count the number of breakpoints, or is there really there is anti-correlation? So in order to address that, I'm finding a problem. So I hope this is my question. This question is clear or still?
Okay, so do you want to, should we wait, break for a discussion here for about 10 minutes?
Or
If anyone has any, or do you want to go to the next problem right away?
maybe I can go ahead first, then maybe I'll present my part then, or
And then we can come back to this.
maybe which one you want to
Unless
say?
anyone has an immediate question that,
Could you elaborate a little bit on the problem itself? Just
Yes. Oh, so main problem what we have is we see an anti-correlation. Solar maxima, we see less number of breakpoints. Solar minimum, we see more number of breakpoints. So during that time, we have two issues. One, so there is we are counting the number of breakpoints in this region, but there is significant amount of region is covered by active regions.
yes.
So basically there is the area available for detection itself is decreased. So we can address maybe taking the density, like how much area is available for detection and number of breakpoint detection. That's what we call X-ray number
Yeah.
breakpoint density. Somehow that can up to one level can address that. That's one issue. Another one what we have is the background intensity itself is increased during solar maximum. So is there still a breakpoints? Just due to the enhance in the background level, we are not able to detect.
Okay, got it.
So those are two issues we are having.
Do you also have geometrical effects? For example, as we do the lean kind of
That's there. That is there.
Where you're in the equator, you will see them better than.
Definitely we have it, but I'm not going to that part. That's definitely we have that.
that could be addressed by just limiting, right now you're looking at the disk up to the 95%
Yes.
of the total disk. If you shrink that area, then I guess you can reduce that effect, right?
But problem when if you shrink more, no, this because we are getting a large number of breakpoint in this region. So if you shrink too much during solar maximum, we get left with very few number of breakpoints because this region is dominated by active regions.
I suppose you could look at specific regions and track what's happening within, maybe just high latitude versus mid latitude and see if there's any difference.
That's also maybe I can show it. I have another one, like I'm not plotted here, but actually that also shows an anti-correlation we have.
I have one other question, just tiny. The darkest of the coronal hole, right? But I see there's some bright points inside the region. Is that common, or is it frequently that you see? My point is, like, if you have a very intense coronal hole, would you be looking at the bright points, or the most the magnetic field is the less bright points, or vice versa? Like.
I didn't get it.
So if you can have the coronal hole is because of the area, but also because of the magnetic field getting out, right?
Yes.
So I'm asking whether there is a relationship between the intensity of the coronal hole and the existence of the bright points inside the structure.
Right now, so this coronal hole actually is not treated differently. It's not treated differently compared to the surrounding region. So all these are actually based on the local background. So the background for source detection, for each region there is a background value calculated, and how much. Then, for example, it's a local thresholding. I would say that.
But you do have access to the background at each pixel. So in principle, you can look at it if you.
Well, the question is, how many breakpoints have you seen inside the coronal holes in relationship with the area? That kind of information that I'm thinking that what happens if you have like a coronal hole that is not that intense and it's comparable to the background? It would not be the same as having a very intense coronal hole and the background. And the breakpoints must have like a different behavior depending on the conditions.
So I have not worked on that, but actually we can do, because I have a coronal hole contour also, so I can consider. But till now I have not looked in that perspective yet.
Yeah, that would be interesting, because what I see, for example, in this plot is that most of the breakpoints are in that area where the coronal hole is a little bit more like restriction in the
Yes.
area size that I do not see in the other section. Right, like
Yeah, I mean, that is the second part of the problem, right? And maybe you're seeing it more clearly because it's dark. Whereas in the rest of it, I don't know if I can point. Well, you know, you can there is stuff here and so on, but I don't know if this were in a coronal hole, you might call this
much brighter.
so it's.
But that would be very interesting to see, no? I mean, because and before getting into the active region problem, maybe the coronal hole will give you an insight of how the
But in all the trains we may not have this coronal holes. Whenever we have coronal hole, then only we can do maybe. It's for example, if I
and if you want me to say why I'm asking also this, have you seen these events? Like I call them the Eye of Sauron, like the where you have the coronal hole, but sometimes you have an active region in the center. And then you have bright points all over, you know, like it's a different image of the.
I'm not saying that
There was an event actually this week.
I have a hole and
an active region in the center.
center of the coronal hole.
Yes. Yes, it's a very peculiar event.
Close by is, but center of not.
Yeah, this week I can show you later the image. But I don't want to keep up, but it's interesting just to discuss them. The bright points and relationships with the coronal.
All right, any immediate questions? Or shall we move along to the next problem? Comments, thoughts from anyone online? I don't see any hands raised or anything, so continue on, please. Adithya.
Okay, so I just put the summary for understanding this number variability is also important for the so how these breakpoints vary, understanding of these breakpoints. So that's also number variability is a part of understanding how these evolve and all those things. And so this intensity due to the breakpoints also can be, if we can understand better, that also can be made part of the solar iridescence modeling, and that can be made much better. And last time, like Federico also had commented that this small scale magnetic field structure has a role in gamma ray emission. So if you can understand these variability even better, the understanding of solar gamma ray emission also can be made much better. They have some issues in those modeling that can be addressed when with if you can understand these small scale magnetic field structures also. So apart from this has another implication I just want to bring. That's all. So we'll go to the next problem. What I'm doing. So here what we are studying is a solar flare precursor. Before explaining what is solar flare precursor, so flare. Let me explain just what is flare. Solar flare is a sudden intense burst of electromagnetic radiation on the solar atmosphere. So most of the time we see in the higher atmosphere, in a coronal height we see that. We also see the chromosphere. The very less counterparts in the photosphere, which is a lower one. So what we try to do is we try to explore the chromospheric image. So observe in an NUV band actually. These data is from recently launched solar mission. It's called Adithya L1. It's the same as my name. Adithya means sun.
What are you named after that?
No. No. Okay. So on board Adithya L1, there is another instrument called Solar Ultraviolet Imaging Telescope. It's called SOOT. So which observes sun in UV bands near ultraviolet. It basically covers the solar chromosphere. So what we are trying to do is there any precursors, like even previous to solar flare, is there any activity can be seen in solar chromosphere, which has connection? We can say through that we can establish a connection, which like a causal connection we can able to establish from the chromosphere to crown the solar flare events. So this is one sample image from the solar SOOT, Solar Ultraviolet Imaging Telescope, which is in a magnesium K filter. This is different filters. So here, for the faster observation, the instrument will go for a surgical ROA mode. This is a region of interest mode. There is one patch of the sun is actually satellite automatically takes only that part of it for a higher cadence observation. So I've shown one such of ROI, so where you can see the active region covered and there is flares coming up there. So this is in magnesium 2K filter. This is a flare what we see. What we are trying to do is, so before the flare, is there any enhancement we see in that region? So that before the flare, we can able to see some previous activities on this region that has linked to the flare. That's we are trying to find it. So in order to do that, what we have done is we have put a small region, this kind of a box kind of thing, and we're taking the total count of this region. Like close to 2 hours before the flare, we just go back, we find the flare and in a data set. So we go back to 2 hours from that and we start to see, is there any activity in that region? So that's and we make a light curve of it. This is a light curve of that region in a one filter. So it actually observes in 8 simultaneous filter, but we are looking only at 2 filter, which is much more sensitive for these active regions. So which is magnesium 2K and calcium 2H.
So what are the other filters?
We have like there is magnesium 2H also. These are 3 chromospherics one. There are another one is something called there are 2 magnesium 2 wings. So we also have 2 wings, 2 cores, 4, 5 calcium H. Another one is another part of continuum actually. There are 2 part continuum actually. Magnesium wings, core, and 2 continuums. And we have a broadbands also. This is a narrow bands property. So here we indicate the flare time using a GHOST catalog. GHOST is it's another soft X-ray instrument. So it classifies the like there is a sudden increase in whenever there is a flare, they have a catalog of all those flares. They provide the start and end time of those flares with in a soft X-ray intensity basis. So what we are doing is a chromospheric is a NUV band observations. So this is the start time according to the soft X-ray catalog, and the solid line shows the peak time according to the soft X-ray catalog. So these are the 2 light curves observed from 2 filters. So we see there are a lot of fluctuations we can see it here. So in order to understand them better, you overplot them together and also overplot the hard X-ray imaging. So red one, what we see is a hard X-ray light curve. See for all these enhancement, what we saw here, these 3, we see that there is a hard X-ray event there. So when there is a hard X-ray, it's a kind of a reconnection event in coronal height. Means it can be a small scale flare, but we are not accounted in a GHOST catalog. It can be a very small flare. So wherever we see a hard X-ray enhancement, we see in a chromospheric enhancement after a slight delay. But except for this event, in one place there are no hard X-ray, but there is we see an enhancement in a calcium. So this time there we could see an enhancement. So there is no hard X-ray coronal height counterpart. So then we went below down. So we looked at the magnetic field in that region. So this is wherever this intensity came from, only that region, we counted the magnetic field in that region. So the green curve dots, what we see is a magnetic field in that region. Above 100 Gauss, below 100 Gauss, we can have some noise region. Up to 40-50 Gauss, we can have a noise level in HMI magnetic field images. So we counted counts above 100 Gauss, and we have plotted here. So in that time, we can see a slight enhancement in a magnetic field in that same time. So that's we see. But if we see for entire region, we don't see the enhancement in that part. So only it's this region is giving out an enhancement. So we suspect that there is enhancement in a magnetic field, means there is a flux emerging happening in that region. So what is this connected to the bigger field, the flaring happen? So we don't know how exactly it's connected. That's one thing we are trying to see. Another one is we see an enhancement, but how significant it is. That is, for example, entire region, it does not show. So we only this particular region shows an enhancement. So what I was trying to see is like how to quantify there is a proper significant enhancement if we have it. So is it like, for example, if we go for in other cases, solar images will have always a good signal to noise ratio. Just going with the Poissonian may not, Poissonian error, if it is above Poissonian error, may not be a good way. So what is a good way to say this is a significant enhancement? So that's one question I was trying to address. Another one is there any causal connection to this enhancement to the flare? That's I'm trying to see. So one way is just looking at about more cases and see is that similar thing is happening. Other than that, is there any other way I can link that to a flaring causal connection, establishing causal connection? So that's the problem what I'm facing. So.
Okay, thank you. So that's the end of the presentation. Good. Comments, questions, suggestions. Let me ask one quick question. So this is, why is it that you have only one such example? I mean, there are plenty of flares.
Yes,
that
yes.
I'm sure Adithya has seen.
Yes, we have. Like I was.
So why don't you see it in other cases?
So this flux, so each flare trigger may not be it will follow the same pattern. There are different mechanisms which can cause the flares. Flux emergence is a one type. So what I'm right now, I'm not looked into the more cases. Right now I was looking about only 10 cases. I yet to increase the number of cases, and still not. There is some other work I start not completed that part. So that's I need to look into more cases. I'm able to say more. But here what I'm saying is these are few questions in like it's not only this particular, like say one enhancement, how I can say that's significant. Few basic questions I had, that also I just try to bring it here. Yes, there are more cases.
And do they show similar enhancement in the night?
Not all cases.
So what made you get to this particular?
Yes, so in this case, so in rest all cases where we have an hard X-ray, we can see there is then this chromosphere will also show response after slight delay. In this case, without any hard X-ray, the chromospheric enhancement we could see it.
So is that the signature that you're looking for?
Yes.
And you see that in like 10 of these cases?
No, I was studying about 10. In 8 cases, I'm not seeing such things. Only 2 cases I could see this one. That's what I went back in the magnetic field. So this is not from the top. If it is from the top, this hard X-ray should show. So maybe from the emerging flux is reconnecting with the chromospheric field and hitting it. That's how we are getting the enhancement in chromosphere, but it's not reached the corona. That's why we are not getting a corona counterpart. That's an hypothesis what we have.
I think Moritz had his hand up. Moritz, if you want to.
Yeah, but you talked about that already. You said how many events are there where you don't see that?
Right.
That was my question, right? But you answered that already.
Okay.
So do you study have you noticed differences in the events besides that? Like, for example, there was a prominence eruption. Was it like several flares going on? Was it only one flare?
So right now, for a simplistic case,
Mhm.
I'm not like any ghost catalog. If it shows like if for any flare, if there is another flare before 2 hours, I'm not looking at that cases as just I can take it as a secondary case. Just that's another flare triggering another flare. It's quite difficult to tackle.
Mhm.
So I'm just identifying the individual flares. There are no significant activity before that flare, at least 2 hours before. Selecting such cases and studying them.
But have you noticed whether there are coronal mass ejections related to that event or not?
So I'm not looked into that coronal mass ejection.
But could be something also playing, because then you have like different ways to release energy. Like when you have the release of a coronal mass ejection, you'll be
Yes.
changing whatever is happening,
Yes.
or whatever it's only a flare. Actually, I heard this Kathy and Luca asking, "Oh, have you seen flares without CMEs?" Or that question.
This M class is the mostly there are. So this one I checked for this flares there is no CME.
Mhm.
So we have both M and X class flare. So there are this is a very M1 class flare.
Mhm.
Most likely there won't be any CMEs. So when I see like M5 above X class flare, then most likely we can have a CME association.
Yeah.
This particular case, there is no CME. I checked this. So there is another case also where there was no CME in that.
You are you likely to see CMEs when you just have active regions just beginning to form? And I thought when you got a flux emergence happening here, presumably.
Yes.
So the active region's on the way up, right? It's not the mature active region, so to speak. Doesn't that affect CME generation in some sense?
I have not looked into that. CME
That's-
is not, but like I don't know.
Yeah, I mean, you probably know more about this, but is it likely? I mean, from the stars perspective,
Yeah.
we know that you can suppress CMEs. We have a very strong feed,
Yeah.
and what I'm guessing is that as the active region is evolving or going up, it doesn't have enough. Actually, that's the opposite argument.
What I would say is this: what I know about coronal mass ejections is that they are very close by active regions, because you have like the close magnetic fields, intensity of magnetic fields. You need to twist the magnetic fields in order to get. But there are kind of evolutions. No, you can have like a prominence eruption. That means that you have enough time to
Right.
create a flux rope. No, that will be condensing material. That's where you can get other elements and chemicals inside. And then that thing is going to be storing energy, and then suddenly will be released. But it's going to be like very pop, no? But then, for example, the Gannon event, the one from May, that we have the northern lights and everything, there was an active region that lasted like 2 rotations of the sun or even more. And the active region was like constantly emerging loops, but like very intensively.
Yeah.
So it didn't have time to be producing the flux rope, but you have a lot of eruptions happening all the time, like that. That's the sort of many eruptions. So it depends on the conditions. That's why I was also very questioning whether it's like you see these events, but it's like a very like done, or it's like 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 making very lots of noise.
Yeah.
No, that would be changing the conditions in the activity, right? Like or like the frequency of the flares also, right? Like how fast they could be produced if you have the conditions magnetically. The other question would be how close the coronal hole is from the active region. No, that will also be playing in.
So that just to if you have a coronal hole close by, it helps to come out.
They are always like mostly they will be like in pairs, because they are opposite magnet one. You will have like a very good scenarios to have the opposition of the magnetic fields, and they will try to pop out. But it depends on the sizes, whether they are going to be nearby or close by, or the configurations. So what happens if you create a CME in the active region and there's a coronal hole nearby? It will be directed or deflected away from the coronal hole depending on the polarity. So it's giving you information about how strong whatever is happening below So I wouldn't not skip it out like, okay, if you're gonna go event like these events particularly, I wonder what was the sun doing exactly at that time, right? What do we see happening, not just in the plot, but in the event
Yeah.
itself, like boom, or as I said, something very like.
Yeah, so maybe in the 8 other cases where you don't see that, maybe it's just a CME.
Yeah.
Yeah, we should.
Yeah, but you're right, maybe there are M flares, right? And there's
Yes.
no CME features,
Yes.
or I don't know.
In this case, there is no like M1 and 2 plus I have. There are 2 X plus flare also I have in my data set.
Mhm.
Yes, I can look.
No
look
CME in any of them?
No, I've not checked for all of the others. I have 2 to 3 only I check for is there a CME.
But don't be very strict, because sometimes also, once you have the CME living, you're also stretching out the magnetic fields, creating current sheets and everything that will also create like the
Yeah.
opportunity to reconnect. So also check like.
But I also am not sure like these are on disk flares, like very much close to disk center. If there is a flare at the disk center and CME, they're like halo CMEs, I'm not sure how
So
to tell like
if it's a prominence, you will see it in 3 or 4, something moving away, no? If it's something like a prominence ejection, even if it's a little bit above, you will have dimmings and features happening in the surface that will pointing out something triggered out. It's not necessary that you will see the LASCO features, but it's also, what I would say is do as most multi-spacecraft instruments that you can. That will give you insights of what the event is happening.
So looking at the AAA image, that will show no dimming if there is
Yeah.
CME.
If it's a 171 or the 195, sometimes you look like something moving. Sometimes it
Okay.
depends on where it was produced. But just take into consideration that whenever the CME leaves, it's gonna be stretching out the magnetic field, and also will sometimes creating enough for popping flares or something, depending on the agents.
All right, good. So this is one of the amazingly a CHASC talk, which actually is ending ahead of time. So unless anybody has any other comments, questions. So, okay, right. So let's thank Adithya again. And I just want to say that all the statisticians who are online, please feel free to contact me or Adithya with any suggestions that you have on specific types of analyses that you might like to see us do. Especially for this causality thing, where I know that it's a massive cross correlation problem. Okay, thanks everyone. All right,
Thank you. Thank you.
bye.
So this is the eye of Sauron for me.
Whoa.
You see
This one you're talking about. Number of bright points here and
well, this is the one. I mean, it's not exactly, this is